Hello everyone, my name is Maxwell Home. I am a third year here at Georgia Tech, and I am in the A4Y group of AE 2610 Intro to Experimental Methods. Today I have a presentation on a recently conducted experiment performed by my lab mates and I on the Rijke tube. The Rijke tube falls into a broader category of something known as a pulse combustor. In a pulse combustor, the combustion intensity and the chemical heat release rate oscillates periodically with respect to time. There are three major parts of interest in a pulse combustor: the heat release caused by the combustor, the oscillations of pressure in the combustor caused by the fluctuating heat release, and finally, the acoustic velocity that is applied to the mean flow rate through the tube. These three major parts are important as they feed off of one another and are able to support one another until a balance is reached and the acoustic input and output of the tube can reach resonance. As previously stated, for this experiment, we will be using a pulse combustor called the Rijke tube, named after P.L. Rijke, shown to the right. As shown in the figure to the right, the Rijke tube is a long vertical tube, open at both ends, with a burner, or some sort of heat release, placed at roughly 1/4 of its length from the lower end. Since this tube is open at both ends, if it is acoustically excited, it will act similar to an organ pipe, allowing the pressure in the pipe to become time-varying and making a neat sound. So why do we even care about this? Pulse combustors actually have some benefits over a normal combustor. First of all, you have better mixing of fuel and air, which leads to more intense combustion. You are also able to transfer much more heat through the walls, as the otherwise present insulating layer of the tube is stripped away by the acoustic velocity, allowing much more heat transfer through the tube. And finally, the pulsations of the combustor will push out any exhaust components that in a normal combustor would have to be dealt with in some other way, making pulse combustors much more simple and privy to reduced heat loss. Now on to the approach. So we'll be using two major pieces of measuring equipment: the piezoelectric pressure transducer, which takes advantage of the piezoelectric effect to measure the pressure experienced at different points of the tubes, and the photomultiplier transducer. The photomultiplier transducer is able to absorb and multiply photons generated by chemiluminescence of the reaction components, and therefore is able to show us the rate at which the reaction is taking place. Fast reactions, more photons, and vice versa. As seen on the right hand, to the bottom right, there are valves that were used in measuring the pressure of the fuel to help modulate its flow rate into the tube. Very similar to if you ever used a propane grill and you have a propane tank allowing the propane into the actual propane grill. And on the top right, we have a control panel that we use to modulate the height of the heat source flow rate into the tube and other aspects of the Rijke tube. And on the left, we have the actual Rijke tube. First things first, we measured the Rijke tube, which ended up being 6 feet. We then hooked up the pressure transducers at 3 different locations on the tube, top, lower, and middle, and then measured the distance between them, which ended up being 18 inches between each of the pressure transducers. After setting up the experiment, we initially took measurements at the base position of 0 inches up the tube, with the valve both opened and closed. Opening the valve caused the flame to become much larger and less efficient, and ceased the pulsations, and stopped allowing it to make the normal sound that Rijke tubes make. But when the valve was closed, it started making the sound again. The flow rate through the tube was increased, decreasing the flame size, making the burn more efficient, and resumed the pulsations. After these measurements, we made sure that the vent was closed, moving the burner to 2 inches above the base position, and took the measurements there as well. We then continued to slowly move the burner up until the pulsations ceased, which happened at approximately 5.6 inches. Finally, although it wasn't measured, we lowered the tube until the pulsations were moved, which ended up being close to 0 inches and not as 5.6, as some people might expect. Now into the results. So the oscilloscope, as previously stated, took data points at 4 points, 0 open, 0 closed, 2 closed, and 5.6 closed. It took 3 major data points for each of these 3 locations. The upper, middle, and lower pressure transducers, where signal 1 is the upper, signal 2 is the middle, and signal 3 is the lower pressure transducers. Anyways, the 3 major data points taken at these 3 locations were the RMS pressure, shown as VRMS, the frequency, and the associated phase. There were 2 data reductions. First of all, we had the relative phase, which was taken from the associated phase relative to the middle pressure transducer by subtracting the associated phase for the middle pressure transducer from each of the other associated phases. The amplitude in decibels was calculated from the below equation, where VRMS equals PRMS shown, and PRMS threshold is a constant shown below. Additionally, using the following equation shown below, along with the data we measured at the beginning of the lab, namely the temperature of the room at 73 degrees Fahrenheit and the length of the tube being 72 inches, we were able to calculate a resonance frequency of the Rijke tube at around 94 hertz. This makes sense, as if you look at the previously displayed graphs, when the frequency is not around 94 hertz, the decibels are much lower, but you see a sharp increase once we hit around 97, which is very close to 94 hertz. Next on to discussion. So there are 3 discussion questions. The first one is what would happen if you have a clumsy friend who breaks the filter, and then you try to use another filter of 415 to 450 nanometers for the photomultiplier. This would not work, as the interference filter is a bandpass filter, only allowing wavelengths of 415 to 450 nanometers to pass through. But this wouldn't make any sense, as the wavelength of the chemiluminescence of OH molecules, which is what we're actually measuring with the photomultiplier in this lab, only ranges between 306 and 311 nanometers, which wouldn't be picked up at all by the 415 to 450 nanometer interference filter. The next one is what would happen if we would actually use hydrogen fuel in this experiment with this same bandpass filter. And that would actually make sense, as through my research online, the chemiluminescence of hydrogen is around 425 nanometers, and as such would not be filtered out by the 415 nanometer filter, allowing this experiment to now be conducted. So after this, to design an actual Rijke tube that would be tunable, as a musician, I had 2 theories on this. So you can do one of two things, or a combination of these two. Firstly, you could have a match ground sliding bell on the upper side of the tube to make it bigger or smaller lengthwise. Or something that also happens with brass instruments is you have to tune your instrument based on how hot it is outside. So you could change the temperature around the Rijke tube to allow it to have a tunable frequency, or have some combination of the two. Finally, on to the conclusion. So I thought this experiment was a pretty interesting one. It was very dissimilar to the other labs that we've done so far, insofar as this material is unfamiliar to me and pushed me out of my comfort zone. If I was to repeat this experiment, I would try to achieve a more in-depth understanding of the material, because as I do understand the material, I feel that the uses and innovation of such systems come from a deep understanding that I'm still working on. In future experiments, I would be interested in testing out different modulation systems for the Rijke tube, such as the aforementioned match ground sliding tube on the top part to alter the frequency, and possibly a change in the temperature. Anyways, that's it for my lab report. I hope you enjoyed, and I hope you have a great day. Thank you.